In this video, I'm going to show you how to design a switching regulator, or specifically a step-down buck regulator. Now, switching regulators can, in theory, can be quite complex to understand. If you look at a data sheet for a switching regulator, you will see quite a few complex equations. So in this video, I'm going to focus more on the practical side. So I'm going to show you how to design the schematic circuit diagram, and then we're going to do the PCB layout. And the PCB layout for a switching regulator is super critical, so you definitely want to pay attention to this. You can't just haphazardly connect up the PCB layout for a switching regulator, and you need to follow very specific guidelines, and that's what we're going to cover in this video. The switching regulator that we're going to be using in this video is the MP2322 from Monolithic Power. This is a 1 amp switching regulator. It's a step-down converter, also commonly called a buck converter, just B-U-C-K. So a switching regulator that steps down, you'll hear the term buck, and then one that does step up, so it takes a lower voltage and goes to a higher voltage, that's a boost regulator. For this tutorial, this video, we're going to specifically focus on a buck step-down regulator. So this one can do up to 1 amp of output current, and it can handle an input voltage up to 22 volts. So what we're going to do, I'm going to scroll through the data sheet just to show you. As I mentioned, designing with the switching regulator, there's quite a bit of theory, it's quite a bit of math that goes into designing one. You can see here, there's a lot of description under the operation that talks about how it operates. There's all these various equations you'll see especially when you get down to select, this one is just for selecting the output voltage, but then there's all these equations for selecting the inductor and selecting the input capacitor and the ripple current, maximum input ripple current for the capacitor. More equations for the input capacitor, then there's all these equations for the output capacitor. So it can be pretty overwhelming. What I recommend, and what I'm going to do for this video just to keep things simple, is I'm going to go with their application circuit, or their typical application. Most data sheets for any type of chip are going to typically they'll give you all the equations and everything you need to know to design using that chip for any type of circuit setup, but they'll usually give you one specific application. So they'll tell you, for this one, it's going to be 12 volts on the input, it's going to be 3.3 volts on the output, and then they even give you the output capacitor that you need, the inductor size that you need, and the resistors for the resistor divider feedback to set the output voltage. So you can see here, this is the typical application circuit, and they tell you it's V in at 12, V out at 3.3, I out at 1 amp. So this is the circuit that we're going to design, and you can pretty much, if you're able to find a typical application circuit that's the same as what you need, so in regards to mainly input voltage, output voltage, and how much the maximum load current. So if you can find a switching regulator that has a typical application that has the exact same conditions that you're going to use, then you can skip a lot of the theory and you can just go into safely designing the circuit based off of their typical application circuit. This tends to be a little bit easier if you're using standard voltages. Let's say you're going from 12 volts to 3.3, for instance, in this case, that's pretty common voltages. But if all of a sudden you were going, 16 volts to 4 volts, then that's going to change all the equation. It's going to change the values of the components they've selected. So in those cases, then you would need to go back and have a better fundamental understanding of all the equations on how to select the components. But in this video, I want to keep it simple. I don't want to get too theoretical and too math heavy. So we're going to just design we're using KiCad, the free open source PCB design software. So basically, I've already designed the schematic circuit for this in KiCad, and let me go ahead and pull that up here. So this is the exact same circuit that is for the typical application circuit from the data sheet here. So it's exactly what they have here is what I have designed the schematic for. Let me just do a quick review on the schematic and the components, and then we're going to jump right into doing the PCB layout for the switching regulator. So you have on the input, you're going to have several capacitors. So they have two 10 microfarad capacitors and a 100 nanofarad capacitor. Then we just have our ground pin, the enable pin, we're just tying it to the input supply. So basically it's always enabled. Then this switching regulator has an internal regulator that it uses. And for that, you need to add a capacitor here, a 1 microfarad to this VCC. Now this is an internally generated voltage. This is not a voltage that you supply. So the voltage you supply is Vn. This is really an output voltage that's generated internally by an internal regulator in the switching regulator. So you just need this 1 microfarad capacitor to stabilize that regulator. Any type of voltage regulator, at least 99.9%, are going to require some type of output capacitor, and that helps to provide a better transient response, but it also helps to stabilize the feedback loop that is created as part of a regulator. And if you don't have this, then what happens is your regulator can become an oscillator, and that's almost always a bad thing, unless of course you want an oscillator. So this is just an output voltage. Then we have our feedback pin, and the feedback pin is how you're going to set the output voltage. This could have been a fixed option. So fixed meaning the output voltage isn't adjustable, meaning that it's only 3.3 volts, for instance, and you can't change that. In that case, for a fixed regulator, just like with a linear regulator, whether it's a linear or a switch regulator, you have this resistor divider, and basically for the fixed output version, they just move this internal. But by having it external, it allows you to adjust the resistor so you can set the output voltage here. So all it does is it samples the output voltage, it divides it down, and then it feeds it back into the part. So this is how the feedback loop, hence the feedback pin, it's how the feedback loop regulates. It has to know what the output voltage is to regulate it to the desired 3.3, and that's what this resistor divider does. This capacitor here is just called a feed forward capacitor. It's basically, it just helps to improve the stability. Once again, I mentioned that anytime you have a feedback loop, you have potential stability issues, which can cause unwanted oscillations, and this capacitor helps in that regard. Then we have what is called the bootstrap capacitor, and this is a 0.1 microfarad, and this just is tying from the BST pin to the switch pin, the SW pin. And once again, I don't want this to be a video on the theory of how switching regulators work. We can talk about that in another video. I really want to just stick to the basic fundamentals of how to design a PCB circuit for a switching regulator. So I'm not going to go into detail on how they work. Then you have an inductor, and this is really pretty much probably the most important component here other than the regulator itself. So this is very important to pick this that matches the requirements for your circuit. Mainly you'll need to calculate the inductance that you need, and for this application of going from 12 volts to 3.3, they've selected a 3.3 microhenry. Also, you need to make sure that this inductor is rated to carry the current that it's going to be seen by supplying the load. So you have to be careful that you pick an inductor that can handle the load. And then we just have a output capacitor. Let me move this. This is actually the 22 picofarad is this feed forward capacitor. The output capacitor is 22 microfarads. And like I mentioned, you have to have an output capacitor to stabilize the feedback loop. It also helps with remove ripple and improve transient response. So the larger this is, the better the transient response, but you don't want to go too large because then it's overkill, and adding like a larger capacitor, larger footprint most likely than is what is actually necessary. Okay, that is it for the schematic. Now we're going to start working on the PCB layout. And when doing the PCB layout, the first thing that you want to do is refer to the data sheet. And the data sheet for most switching regulators will give you an example and guidelines on how it needs to be done, because you have to follow the PCB layout guidelines very closely they'll give you guidelines, and then most of them, at least the good ones, will give you an example PCB layout that you can pretty much just follow. And I would encourage you to stick with a switching regulator that has a data sheet that gives you that example layout. That's going to make things a lot easier for you. And I don't know the exact percentage that have. Most switching regulators tend to have an example of the PCB layout since it's so critical, but I know all of them don't. I've seen some that don't. I would encourage you to try to find one that does have that, just to make your life a bit easier. Okay, so let me see where, yeah, here it is. So they give you the PCB layout guidelines. Let me just quickly review these. Place the high current paths, so ground, input, and the switch. You want to place those very close to the device. You want to keep really short, wide traces. And in fact, for a lot of this, we're not going to technically use traces. We're going to use what's called a copper pour. We'll just draw an outline of a huge piece of copper instead of just drawing individual traces. Add more vias on the ground plane. Place the input capacitor as close to in and ground as possible, so as close to the input and the ground pin of the regulator. Place the feedback resistors, so R1 and R2, close to the IC, and then connect a VCC capacitor close to VCC with a short direct ground trace. So those are their general guidelines, but here is their example PCB layout, and this is really where I think the most value comes. So you can see the way that they've done this. They show you how to place. These are the input capacitors. This is our output capacitor. This is our bootstrap capacitor. This big guy here is our inductor. Then we have our feedback resistors here. This is that small feed forward capacitor for improved stability. And then here is the 1 microfarad capacitor that goes on VCC, which is the internal regulator. So for most of these, what you can see is they're not traces, they're big blocks. So for instance, all the input capacitors and the output capacitor here all connect to ground, and they need to tie into the ground pin of the part, but they also need to tie into your ground plane on your part or on your board, and that's why they have these vias here. I would encourage you to maybe even add more vias than this to connect it to the ground plane. But you can see they have this big block here, so all of this is ground that connects it. It actually comes down and grabs also C4, which is the VC capacitor, so it grounds that. And it also grounds R2, which is the resistor divider for the feedback. So all of that is with this. So you just basically, as we'll see in KiCad, you just draw an outline and then tell it to fill it in with copper. Then we have V out here. So this is also another big block. The main things that you have here are you just have the inductor and then you have the output capacitor. Those are the high current things. So all these big copper pours are mainly critical for anything that's high current, just like it said here at the very beginning. High current past ground, input, and the switch. What you see here, this blue line, is actually a trace, and what it's doing is it's a low current. This is just the feedback sense. So all this is doing is measuring the output voltage and feeding it back to the regulator so the feedback loop can regulate it. So it just ties here into the resistor divider. Now there's no current, there's very little current. It's microamps of current that flow through this. So this does not need to be a wide trace or a copper pour or anything like that. It can just be a minimum width trace. The same here for connecting up the resistor feedback and the capacitor. They have a wide trace here, but that's not necessary. You could connect those with a minimum trace because there's just no current that really flows in any of this here. You can see they've also done a trace. It's short. You want C4 placed really close to the VCC pin, but you don't have to get too fancy with a copper pour for that. They've just used a trace to connect that capacitor, but it is critical that you have that close to the capacitor. Then we have the input, which is another high current net. So this is also just a big block copper pour, and it grabs the 3 input capacitors and then grabs the input pin. And then we have our bootstrap capacitor. This is C3, which ties from the bootstrap pin to the switch pin. And keep in mind that the switch pin or the switch net was one of the high current nets that we need to use a copper pour for. So here we have our third copper pour, or actually the fourth, because you have ground, V in, V out, and then the switch here. So this copper pour grabs the bootstrap capacitor and it grabs the other side of the inductor. And that forms the fourth copper pour. Okay, so that's a review of their suggested PCB layout. Now we're going to jump over into KiCad and design the PCB layout step by step. Before we get started on the PCB layout, one thing I've done is just change the reference designators to match what was used in the reference circuit. So for instance, I think initially I had the bootstrap capacitor as C5 and I've changed it to C3. And basically just, I wanted to make sure that we keep the same reference designators as they used here. Otherwise it gets confusing and we're going back and forth and their C2 is different than my C2, for instance. Okay, so here we have the schematic, and let's go ahead and now we're going to convert this into a printed circuit board layout. So I'm going to go under Tools, Update PCB from Schematic. This usually takes a few seconds to run. Okay, I'll do Update PCB, close it, and then here are all my components. So I can now zoom in. So what we're going to do first thing is we're going to place all of the components just like they have placed them here. So let's start with the chip itself and make sure that we've got pin 1 in the top left corner, and then we have our input capacitors. Okay, so I'm going to grab this, move it down here. Let me zoom in. And yes, you can see we've got pin 1 in the top right corner. Let me also maybe move this down here where it's not overlapping it. Now we need our input capacitors. Let's just move. Okay, so C1. Actually, I'm going to make a little more space. Let's move this guy way down here and we'll start there. Okay, so C1, C1A. 1, slightly different. They just called it C1A. I've got C1A1. And then let's do, if I can, there we go, these here. Okay, so what we're going to do is rotate these around. Let's go back here. You can see that here we're going to grab the ground. So we want the ground at the top and then the input on the bottom. Okay, so I'm going to take this guy here, rotate it around, and I'm going to put it as close as I can right there. I'm going to just get rid of the values here just to make a little more room. Okay, we'll leave the reference designators there. Okay, then we have our C1 capacitors. I'm going to rotate that around. Then we have the C1A, rotate that around. And I'm going to put these kind of down here just to get them out of the way. And let's move all these as close as possible. Okay, there's our 3 input capacitors. Next we have our, let's do the C2. So that's going to go from ground also to our output. So let's find C2, that's this guy here. This is our output capacitor. And we want ground to be on this left side, so I'm going to just rotate it around, get rid of the value again, and let's move this kind of over here. And this we're going to have right here in the middle, up here. Then we have L1, so we want L1 with the V outside at the top. Let's find L1, here's L1. And we're going to rotate it. Oh, okay, so 3.3 volt VDC, that's what I named that terminal. So that's our V out. So let's do that here. Let's move that up there. And we I'm not sure why this reference designator is a smaller font. That's a little bit more of a realistic font size. Let me just get rid of the value here. Okay, so let's go back here. And then we have also our C3, which is our bootstrap capacitor. And we want that to go from, we want it switch on the top and the bootstrap terminal on the bottom. So again, let me just get rid of the value there. And we're going to have to squeeze that in here. So we're probably going to have to move over the inductor. Let's just put this kind of like that. This down here. Let's move that like that. And I think we're still okay here, but let's just move that down a little bit too. Okay, let's go back here. We've got input capacitors, output capacitor, output inductor, bootstrap capacitor. So those are the most critical components. Now we just have basically our internal regulator capacitor and then our feedback voltage voltage divider here. Okay, so C4, let's go back here. C4, this is going to go to pin 4. So I'm let me get rid of the value again to do some shuffling here to get these reference designators not in our way. So we'll put that here. Let's see. Yeah, they've actually got it here. So the ground comes underneath the part and then grabs those. So what we could do is just move this over a little bit more. Like that. And to do something with these, let's just move that there. And let's just, I don't know, we'll move these up here for now. There we go. And then we just have pretty much our resistor dividers. So we need R2. And we want R2 ground on the left side here. So I'm going to rotate it around, get rid of the value there. Okay, let's R2 there. And then we need R1. And we want this one rotated as well. So the feedback net is right in between them. Get rid of the value again. And let's move that here. And then we have our C5, which is the feed forward capacitor. This guy here. And let's move this reference designator there, get rid of the value. Move that like that. And we're going to need to rotate it because we want it's just in parallel with this R1. Okay, move that back there. Okay. And then the only one left is R3. Let's go back to our schematic here. I think I maybe forgot to mention R3. So R3 is just a pull-up resistor. So PG it's very common. You'll see on voltage regulators, whether switching or linear regulators, you'll see a PG output pin, which is power good. So this basically goes high to indicate when the output is in the regulated range. So for instance, most regulators will have a soft start. So it takes them a little bit of time to reach the regulated voltage. And you don't want to typically, it's supposed to be 3.3 volts and it's slowly ramping up there. You don't want to feed that ramped up voltage to all of your circuits because they may misbehave if they see the 1.5 volts as it's the intermediate voltages as that is going up. So the power good typically is used to make sure that you only use the output of the regulator once the power is actually good, which means it's reached its regulated voltage. And this is an open drain output, which means that it can pull down, but it can't pull up. So it needs a pull-up resistor. So this 100K ohm resistor is just a pull-up, and it's pulling it up to the internal voltage, regulated voltage, or VC that we've already discussed. So that's R3 here. Okay, and R3 is one of those that does not matter. It's wherever you can find that it will fit the best. So we've got our PG pin, I think is this pin here. So we just need to make sure that I don't think they show, yeah, they don't show the PG pin, but we'll just maybe put the pull-up resistor over here somewhere and we can just route like right out there. Okay, I'm gonna actually move this up a little bit more. Move this up a little bit more. And then that way we can just easily grab the PG. Let me move this up just a little bit more, okay. So I'm gonna just move R3. Let's maybe move this designator there, get rid of that value. And we can just put R3 in here. But like I said, it doesn't matter. I could put R3 on the other side of the board and it would be fine. Okay, PG pin, okay. So there we go. We have all of our components placed and now it's just a matter of drawing the copper pores and then connecting up the few traces that we have. Okay, before we begin doing the copper pores and connecting everything, just to make things a little bit more clear and not quite visually so distracting, I'm going to get rid of all the reference designators. Since we're not doing a full PCB design, you would obviously want these on your board normally. Okay, so now we can just focus on the components themselves and not be so distracted by all the text. Okay, so the first thing we're going to do is we're going to do a copper pour. In KiCad, it's called a filled zone. I tend to call them copper pores. So I'm going to select here. First thing you're going to do is you're going to just left click one point. Then this menu pops up and you have to tell it what net this copper pour connects to. We're connecting it to ground. This other stuff here, most of this the clearance, this is basically how close the copper pour is allowed to get to other metal that it doesn't connect to. And then this is what's the minimum width that the copper pour can be. I'm going to just set these both at 10 mils. And pad connections, it defaults to thermal reliefs. We're just going to do solid. And then everything else you can keep the same. Once you click OK, now you can finish drawing that copper pour, knowing that it's going to be connected to ground. Okay, so there is the ground copper pour, and it's not filled right now. If I right click on the edge of it and go under zones, then I can do fill all zones. And now you can see it's filled and it fills in and it grabs the ground pads for the 4 capacitors and the device itself, the ground pin. Okay, next we're going to connect C2 and our inductor with a copper pour. Okay, so we've got our C2, let's see here, first of all, I'm going to unfill this all zones. Okay. And what we're going to do, let me move this maybe down a little bit. And we're going to also probably need to move that up. I'm going to move it right to the edge of the copper pour for the ground so I don't have to redo that. Okay, so now we just need to draw a copper pour for our 3.3 volt net, or this is our V out. So I'm going to do place, filled zone. I'm going to start it like right there. And I'm going to select, I want it to tie to 3.3. Change this back to 10 and solid and do OK. Okay, now we can come over and grab this. Okay, there we go. And let me just show you, let me do a fill all zones. And you can see once again, it's filled this in. Okay, so I'm going to go ahead and unfill them. Okay, next we have our switch node, which is this right here. Let's just go back to so we're just going to connect this here, and then we have to grab pin 8. Okay, so once again, place a fill. And actually, before I do that, I still need to move this guy down a little bit more. Good. Okay, now let's do place filled zone. So I'm going to start it here. And this we're going to do is this net here, the switch net. And once again, I'm going to just set this all like we have in the previous ones. Okay. Okay, so now I'm going to move this, come over here, grab that. And these lines don't have to be perfectly straight. Okay, there we have that one. And let's see what else we have. Let's go back to our reference. So we've got this. We did not come in here and grab the grounds for C4 and R2. Let's take a look at that here. Yeah, probably what I'm going to do, instead of necessarily a copper pour through here, you could just, because even C4, these are all fairly low current, so it doesn't really have to be super wide. So we'll just see what the widest trace we can get there, and we'll just tie it from the ground pin here, and then we'll just route down to here. There we go, so we've got that, and then we'll just draw another, just tie these two together like that. And we can connect these two together. This goes here. This is our top resistor in the divider. This is the feed forward capacitor. Okay, now we just need to place our last copper pour for the VN, which is going to grab the 3 input capacitors and our input pin here. Keep in mind this says VN, but this is really the enable pin, which we've just tied to VN. So this is not critical. This is no current flow through this, so we can just connect with a trace. We'll just tie that to our VN copper pour. Okay, so I'm going to do a place of filled zone, and I'm going to start, this pin here, and we want to tie it to VN. I'm going to do clearance again, 10, and set that to solid, and go. Okay. Now we can draw the copper pour. And actually, I'm going to just go ahead and include the enable pin in the copper pour. That way we don't have to draw another trace. The only reason that could be problematic is if you wanted to all of a sudden, say, modify your board, just to modify it after production. If you wanted to tweak it so you can, say, control the enable pin and disable it, well, if you just have a separate trace, that can be a little bit easier to get in there and cut and modify a board. It's really hard if it's part of a copper pour, but that's pretty minimal. Okay, so I think that I'm going to go ahead and do a fill on all of our copper pours, and let's see what they all look like. Okay, so there we have our 1, 2, 3, 4 copper pours, and now it's just a matter of the only thing left is we have to connect up our bootstrap capacitor. So I'm going to go ahead and let's move that up to about there. And now I'm going to just do a trace from like that. And then the only thing left that we need to do is to grab our feedback. And then we have to squeeze through and grab this EG. Okay. That is our finished layout. Let's just check. We have our ground plane or our ground copper pour. We have our V out copper pour. Oh, one last thing that we need to do is we need to, from our feedback network, needs to tie into the V out. So I'm going to just draw it from here. And once again, this is one that is not critical because there's no current flow. It's just like a sense voltage. Okay, so that's our output. Then that feeds into our feedback network, which feeds into the switcher and allows it to regulate. And the only other thing we have is we need to connect up our VC for the capacitor, which is just the internal voltage regulator. Remember, it's not the supply that you're supplying to the part. If you found this video helpful, then definitely check out this video here, which is a masterclass workshop showing you how to design an entire electronic product, including both the electronics and the enclosure design.